This lesson is focusing on functions past paper questions, continuing on the theme of unusual questions rather than standard questions. So of course, when it comes to functions, we're going to be talking quite a bit about domain and range. So the first question we have today is actually a special request question. The function f is defined for x is an element of all real numbers by f maps x onto x squared plus ax plus b, where a and b are constants. Nice and straightforward, we have a quadratic. In the case where a equals 6 and b equals -8, find the range of f. So we're just going to start by just rewriting our fx equals x squared, a is 6, so plus 6x, b is -8. Find the range of f. Well, we have a happy quadratic, so in order to find our range for all real numbers, we really need to locate that vertex. Best way to locate the vertex is to complete the square. So fx equals no coefficient of x squared other than 1, so straightforward. X plus a half b all squared minus a quarter b squared plus c. And then we can simplify. Fx equals x plus 3 all squared minus 36 over 4 minus 8 takes us then to -17. So once we have completed square format, we can of course pull our vertex straight out. Vertex equals, change the sign, keep the sign, -3 minus 17. So our curve is a smiley face as we established. Vertex is -3 minus 17. The range will be going up from the vertex, so up from our y value. So our range is f of x is greater than or equal to -17. Everything above that vertex is a valid output for this function. Part 2. In the case where a equals 5, the roots of the equation fx equals 0 are k and -2k, where k is a constant. Find the values of b and k. There's quite a lot of information here, so let's start by breaking it all down. We know that fx equals x squared plus ax, and a is 5. So plus 5x, we don't know b, which is one of the things we're looking for. So plus b. So we have now fx. Now they tell us the roots of the equation. So fx equals 0, then the roots are k and -2k. So if we had x squared plus 5x plus b equals 0, our answers would be this. But remember, when we have the answers, we can also work backwards. So we would have x squared plus 5x plus b equals 0. Well, we can't factorize when we don't know what b is, but we can work from the answers back up and see what we get. So given the roots, we know then that x minus k, x plus 2k equals 0. When we factorize this, this is what we would get. Okay, remember that you've got to change the signs when you put them into brackets because you would change the signs coming out. So just check, x minus k gives us x equals k, x plus 2k gives us x equals -2k. So we're happy. Now we can expand. So x squared minus kx plus 2kx minus 2k squared equals 0. Combining some like terms there in the middle, x squared plus kx minus 2k squared equals 0. So now we have two quadratics that are equated to 0, and that are the same thing. Because we've got the starting point of the equation and we've got the starting point of the equation. We've just worked from two different directions. What that means is that x squared is x squared. 5x is kx, and therefore k equals 5. So comparing coefficients, we would then be able to see that k equals 5. We can carry on because, of course, if our constant term in our first equation is b, and our constant term in our second equation, which is the same equation, is minus 2k squared, we know that, we know that b equals minus 2k squared, but we've got a value for k. So b equals minus 2 times 5 squared, b equals minus 50. So we were asked to get the values of b and k, and there they are. K is 5 and b is minus 50. So we're working from all the information that we're given in the question to get to something we can look at and in this case, compare. The next part of this question is slightly more interesting again. Show that if the equation f of x plus a equals a has no real roots, then a squared is less than 4 times b minus a. Okay, right. This looks just odd. We have never worked with any weird things like that before, but there's things we recognize. F of x plus a. We're just going to put x plus a everywhere there's an x. Okay, equals a. We're going to equate that statement to a. No real roots. Discriminant. So, no real roots, we know b squared minus 4ac is less than 0. And then maybe we will get to something that will start to make sense. So whenever you're faced with a question that looks just really odd, don't give up and throw your arms up in desperation. You do have the skills and you do have the techniques that you need to answer the question. And it's a case of working through and seeing what happens. So we know our original equation is fx equals x squared plus ax plus b. Okay, we don't have values for a and b. So now we're going to do f of x plus a equals x plus a squared plus a, x plus a plus b. Substituting in that x plus a everywhere there was x. So, x plus a all squared, x squared plus ax 2ax plus a squared plus ax plus a squared plus b, not forgetting him at the end. We've got some like terms going on here, so let us combine them. So we have x squared, 2ax plus 3ax, a squared plus a squared plus 2a squared plus b. So now we have a relatively simplified quadratic. Lots of a's and b's going on, but we can still keep track of them. Now we need to get this equals to a, and we need to then move towards our discriminant. So a equals x squared plus 3ax plus 2a squared plus b. Well, before we can use a discriminant, we have to make it equal to 0. We must have a quadratic equal 0. 0 equals x squared plus 3ax plus 2a squared plus b minus a. Now we need to go for no real roots. That would be our next logical step in solving an equation like this. B squared minus 4ac, but we've got lots of a's and b's that we're playing around with here. So let's just make sure we're clear with the a, b's, and c's for the discriminant. So a would be 1. Our b is 3a, and our c is 2a squared plus b minus a, because all of these are constants. Okay, so when it comes to discriminant, a is the coefficient of x squared, b is the coefficient of x, c is your constant term. So in this case, no real roots. B squared, 3a squared minus 4ac, 2a squared plus b minus a. The whole thing is c, so the whole thing must come into your discriminant. And no real roots less than 0. Now we open up. So 3a all squared, 9a squared minus 8a squared minus 4b plus 4a less than 0. And we're starting to get suspiciously close to the thing that they gave us at the beginning that was all just gobbledygook, that a squared less than 4 times b minus a. 9a squared minus 8a squared is a squared minus 4b plus 4a less than 0. Well, they want a squared on its own, so a squared less than 4b minus 4a. They want the 4 factorized, a squared less than 4b minus a. And magic, by working through a simple case of substituting into a function that's given, equating that function to an a, getting to n equals 0, and then applying your discriminant, 3 things that you are very comfortable with, you have shown the weirdness and ugliness that was present in this question when you started. So it doesn't matter how odd and how strange the question looks, they are still testing those same key skills, those same key techniques that you've always been doing. So it's just a case of using those skills and techniques in this weird and wonderful question and then letting the magic happen. Have we got any questions, or does this question and this use of all these techniques make sense to everybody? Okay, we have lots of happy people, so let's carry on to our second question for today. These are rather large questions, so we're only going to be working through 2 of them today. Moving back to 2014, this question starts out nice and straightforward. Express x squared minus 2x minus 15 in the form x plus a all squared plus b. Completing the square, we can do this. So x squared minus 2x minus 15, x plus a half b minus 1 all squared, minus a quarter, b squared is 4 minus 15. So x minus 1 all squared minus 1 minus 15 minus 16. Done and straightforward. So now let's have a look through what else is coming. The function f is defined for p is less than x is less than q, where p and q are positive constants, by this very familiar quadratic. The range of f is given by c is less than f of x less than equal to d, where c and d are constants. So in this case, we don't know the domain or the range. Right, so first up, say the smallest possible value of c. Okay, we can work towards that. For the case where c equals 9 and d equals 65, find p and q. So if we give you the range, what's the domain? And then find an expression for f to the minus 1 of x based on that range and domain that you worked with. So, do you understand domain, range, and inverse of quadratics? That's what this question is really getting to grips with. So we know here that x minus 1 all squared minus 16 is the same as our fx. So, fx equals x minus 1 all squared minus 16. So if we were to sketch our curve, it would look like this, and our vertex would be 1 minus 16. Now what we're saying is that is the full curve. That is for x is any real number. Now they are saying that we are restricting this domain. We are taking just a piece of the domain. Okay? What piece could we take? If our range is going to be affected, so if we cut out a piece of the domain, we could have a range like this to this, and that would be the entire piece of range. Okay? Or we could cut slightly different, and we could have a range from here to here. Now this is our range, depending on where we cut that domain. So the smallest possible value of C is the smallest possible range value that this graph could have. So the smallest possible range value ever, irrespective of where we cut it, would be minus 16. It would be the vertex of that graph. So our smallest possible C equals minus 16. Okay, so minus 16 would be our smallest possible C. So, next one. Now C is more than 16. C is now 9 and D is 65. So we're not working in terms of the bottom of this curve. We're now going to restrict. So we could have, let's just draw it a little bit flatter so it's easier to see. Let's say that C is 9 and D is 65. So this is our range. So we could be cutting here and here, 9 to 65. Okay, or we could have it on the other side, 9 to 65. However, they told us, and this is why every piece of information in here is important, P and Q are positive constants. Now we know that this point here is x equals 1. So in order to work with P and Q being positive constants, we must be working with the right-hand side. This side doesn't exist. Okay, so we want to know, what would P and Q be? What are the domain values that respond to the restriction that gives us a range of 9 to 65? So we need to set up some way to solve for this. So we know that our range is from 9 to 65. So we know that 9 is less than or equal to f of x, which is less than or equal to 65. So 9 less than or equal to f of x was x squared minus 2x minus 15 less than or equal to 65. And then we look at that and we say, oh my word, we can't factorize quadratics and solve them unless they're equal to 0. We have never done quadratic inequalities with 2 inequalities. However, we have learned all sorts of other wonderful skills. We know that if we want to solve inequalities like this, we have to do the same thing to each piece. We also know that at the beginning of this question, they asked us to put this function into completed square format. Now, there must have been a reason. If we put this into completed square format, x minus 1 all squared minus 16 less than or equal to 65. Now we've only got one x to deal with. Now we can actually solve this same likely we would at IG. We're going to get rid of the 16. We add 16 to both sides. So 9 plus 16 gives us 25. Less than or equal to x minus 1 squared less than or equal to 65 plus 16 gives us 81. Now we have two beautiful square numbers and a x minus 1 all squared. So in the same way that we could square root both sides of an equation, we could square root each piece of our inequality. We also know that we don't have to worry about plus minus because we're only working on that positive side. So as P and Q both greater than 0, positive roots only. So square rooting. Square root of 25 is 5. Less than or equal to x minus 1 less than or equal to 9. Now we can get rid of that 1, add 1 to each zone. 5 plus 1 gives us 6, less than or equal to x, less than or equal to 9 plus 1 is 10. So we have worked backwards from our range all the way to our domain. So our domain statement is p less than or equal to x less than or equal to q. So therefore, p equals 6 and q equals 10. So we now have a domain and range for this piece of our quadratic. Happy. So moving on to finding an expression for the inverse function. We know that f of x equals x minus 1 all squared minus 16. Quadratic's inverse completed square format is the place to be. So y equals x minus 1 all squared minus 16. Doesn't matter that we're working just with a piece out of our quadratic. Okay, so let's have a little reminder here that we're going from 6, 9 to 10 and 65. That's just the piece we're working with, but it's still a quadratic, so we're still going to work through the same steps. For inverse, swap those around. X equals y minus 1 all squared minus 16. So x plus 16 equals y minus 1 all squared plus or minus the square root of x plus 16 equals y minus 1. So y equals 1 plus minus square root x plus 16. Then we take a look. Remember that the range of your inverse is the domain of your original. So the domain of the original was from 6 to 10. So we need to add on to 1. 1 is not big enough. So therefore we know that f to the minus 1 of x equals 1 plus the square root of x plus 16. So it's exactly the same techniques. It's exactly the same approaches. Doesn't matter that we've cut out just a random piece of this quadratic. We still work through everything else exactly as we would do for a bigger piece of a quadratic. Any questions about this or anything else related to functions? Okay, so questions come through about solving inequalities when there's two inequality signs. Just a recap of that. Okay, so let me, okay, I don't have much space. I shall use this space here. So at IG, you will have come across inequalities like, who knows if this is going to help work even. 12 is less than x plus 3, which is less than or equal to 5. Okay, we'll keep it simple. So in this case, you have x only in one place. So what you would do is you would then just work with those 3 zones in the same way you'd work with 2. You treat them exactly the same. So you would have a minus 3, and you would have a minus 3, and you would have a minus 3. What you do is you're working with exactly the same rule of treat everybody the same. So 12 minus 3 will give us 9, less than x, less than or equal to 5 minus 3 would give us 2. So we would solve our inequality. The other way we do these things, which ties quite nicely into the next question that's come through, if we had something like 2x less than or equal to x plus 6, which is less than x, 2x plus 10. Now this is getting far more complicated. Now we've got x's in different places. And we've hit that same problem as we did here when we tried to put a quadratic in. Can't deal with all those x's. So in this case, you would actually split this into 2 inequalities. So you would solve 2x less than or equal to x plus 6. And you would solve x plus 6 less than 2x plus 10. So in the same way here, you could have actually solved this with two separate equations. When my range is 9, what is my domain? When my range is 65, what is my corresponding domain value? It's just simpler and more efficient to do it all as one. So in this case, we go through the same thing, subtracting x from both sides. So we would have x is less than or equal to 6. And I think I've got myself a problem here. Okay, so this is what happens when you do things back to front. Yes, I have. Okay, I'm just going to rewind quickly because what I need is my 2x in the middle. I think that's going to work a little bit better. So 2x plus 6. So x less than or equal to 2x. So 0 less than or equal to x plus 6. X greater than or equal to minus 6. And on this side, we also need to move that 2 for this equation. So here, we would have minus x. So we would have x plus 6 less than 10. So x less than 4. And now you can see how it's worked nicely because x is greater than or equal to minus 6, but x is less than 4. So we can bring them back together. So we took them out to solve them each. We bring them back together, minus 6 less than or equal to x, which is less than 4. So that's your two different approaches, your two different sort of styles of solving the linear inequalities when you've got two zones. Either you work 3 zones all the way, do everything, or you split them into 2 zones, solve them separately, and bring them back together. So the same thing applied here. When you got here and got stuck, you could have split it into 2 separate equations and solved for your 2 domain statements. But again, it's all about efficiency and it's all about simplicity. And so to put it into that completed square format gives you a much quicker, more simple, more streamlined way to solve for those values of P and Q.